So I've got a new direct drive rotary motor from ALVA. They're from Norway. Um, Everybody's smiling. So they're very happy. They know how to party. So I would be partying too. You don't have to wind these by hand anymore. They have a machine that does the winding. It's unbelievable. It's like a giant sewing machine that bangs out the winding. So no more little old ladies sitting around doing the windings for us. Got to get a machine to do it. Um, yeah, Norway. It's a very thin motor. There's a magnet and a coil. Um, they have a lot of really cool technology in this motor. Very precise. Um, so the magnet is a stator. Um, the magnets rotate. The stator stays. So the magnets use a Halbach technology, so get a lot of torque to your coil. I'll explain that in a minute. The really advantageous feature is the low torque ripple, like less than 1%. So I measured like 100 milliamps of cog out of like a 20 amp motor, two and a half continuous, maybe 20 peak, but very low, very precise, very smooth. You rotate it by hand, and you can see that it just feels smooth. So we've got the motor here, and you turn the shaft, and it just feels like butter, so smooth. There's also feedback on it here connected to the AEV, so we'll take a look at that too. Yeah, so large peaks for a short period of time, very smooth, low cog, all kinds of great applications for low cog. So we're going to say near zero cog. You might as well say zero cog, but I'll say near zero cog because I did measure a little bit, but it really is nothing compared to some of these other motors, like the Genesis motor, which got bought by some rich billionaire and put out of business. That thing had 1 cog per rev and lots of cogs per pole. I couldn't even use the cog compensation because it was misaligned. And I can't send the motor back because the billionaire bought the company and shut it down. So anyways, I'm just complaining. So I got the RLS here, and there's a wiring diagram, and you can see the shield goes to the Copley, not to the motor case. That's excellent. So brown is +5, ground is white. The clock is the master red, and the knot is blue, and the data is the SLO slave data back on the data input, green and yellow. So that's how you wire it to the Copley drive. They got great data on their webpage. So between that and one of their specy sheets, I was able to put all the data together that I needed to get this thing set up and configured. So slim torque motor. And so this is a kit, so this doesn't look so slim, but it's all built up in there. Bearing and feedback device. There's the RLS. And really smooth bearings. That was nice. They present some good data, mechanical data here, and then Renishaw RLS has the good data about theirs. It's the 20-bit, so it's like 1 million counts per rev. So we'll take a quick peek at the basic setup. So it's a brushless rotary motor. There's no brake. It's a BIS, okay, and it's 20-bit, and I just used the defaults. All the Renishaw seem to work with the defaults. Don't ignore your feedback. If you get CRC faults, fix your cable and grounding shielding. Don't ignore your feedback. Mine worked first time, no problem. So I'm very confident that we can do the good cable and grounding shielding. If you had a break or need to come to a controlled stop, you can set the times to stop. There's no break, but we can hold the load, make it stop bouncing around, and then cut the H-bridge. Cut the H-bridge for safety after you've come to a controlled stop, so nobody dies from a flying inertia or something. CAN, that's good mode or EtherCAT, and this is just a CAN drive. And so I entered the data for the motor, ALVA with a good part number. It's 36 poles. I think that's in one of the spec sheets, but I measured it. I had 36 divided by 2. positions that it's stuck to. So you can count the number of detents or electrical holding positions and then multiply it by 2 and get the number of poles. And so this motor has some inertia. The continuous is 0.63 Newton meters. The peak is like 6.3, so 10 times bigger. But I just set it to 3 times just for my own safety and trying not to spin it off the table here. You get the torque constant, Newton meters per amp, and there's the RMS version. There's the peak version. Some motors are normally rated amps RMS. And then you can switch to the back. It's like 24 volts per kRPM. It's got a higher resistance for such a low inductance. So yeah, 16 kilohertz, twice that for the ripple frequency. We'll want to double the PWM just to keep the ripple currents down. I'm actually surprised I was able to tune this without a short circuit. The motor can go fast. You'll need like 150 volts to get there, but you could calculate initial tuning parameters, but I did the tuning myself. We'll take a look at the bandwidth, 100, 200, 300. They're starting to roll off, so 500 hertz. There was a little crossover distortion. I didn't want to crank the gain up too high, so there's the continuous. And again, peak 3 times the continuous, but you can go up to 10 times. This drive will do 30, so you can do that all day. Maybe it's several seconds for peak current, so the drive can do that. Just don't burn up your motor. With the I2T algorithm, we will not burn up your motor, so no need to worry about it. Let's take a quick peek. I got 48 volts here, so I can go 2,000 RPM, but we'll take a quick peek at the tuning. So I apply to the current, auto. Yeah, let's look at the small current. This is 10% of the motor's continuous current. It looks a little bouncy around there, but let's take a look at, oh, yeah, okay, so let me go back. Current again. Let's do the sine wave, just so we can see the crossover distortion effect. Not bad. Let's increase the current. We'll do 2 amps, so more of a continuous rated current. Yeah, there's a little crossover distortion as you go through 0. The PWM has a little bit of a dead band on it, so low inductance, that's what you get. Add some inductors, that'll go away, but it's not going to affect us when we make precision moves, so that should be fine. And then, of course, tuning up the velocity loop, auto setup checkbox, bang, 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 5 times a second. Let's slow this down. Let's do it 2 times. So it's got a little larger inertia. I set some limits here. I'm going to have to hold this thing down because it might rock off the table. I haven't bolted it down yet. Okay, so there's a little compliance with the rubber pad that I'm on. Seems to be okay. I'll let go of it. So there's the tuning. You know, just flat, flat, flat. A little bit more integral perhaps, but it was interesting. If I normally for a large mass or inertia, I might bring this down to 100 hertz. But there's no load here, and this thing is kind of like a direct drive, linear but in the round kind of motor. So I was able to, yeah, with too much gain, you might get a little bit of buzziness here in the velocity loop. So let's just see where that comes in. There it goes. All right, gain's too high. All right, move the pole out. There, now it's just not the same oscillation, but at a higher frequency. So gain margin and phase margin are very related. So you can see a little oscillation there. So the gains are too high. So cut them in half and get rid of that. And it didn't seem to matter where the pole was, 100 hertz, kilohertz, big inertia, put it at 100 hertz. Low inertia, low mass on the inertia on the system, low mass, you know, you can do a kilohertz and you can get some pretty incredible position loop gains out of it without bouncing around. So this is just a trajectory move, 1,000,000 counts, and auto setup checkbox. 1 pair of magnets. 6 of those. Trajectory limits, 1,000 RPM. Let's look at the current. And we'll see that this has a very low. Okay, so there's a single rev move. I better do a longer move. So this would be a short little move. And we'll do 10 revs, maybe a little longer time. I got a little excessive noise in the current loop here. I'm just going to turn the gain down a little bit. And never have more bandwidth than you need. So just bring those down together as a percentage. I'll just do 100 hertz just to keep the, ooh, there's the oscillation. There. Yeah, that's it. Yeah, so with a high PP, set that back down. All right, this is for a large mass. Okay, and there's the move. To get the higher proportional gains, I need to move the pole out. So that's a good lesson. And so while it's moving, I got an error plus or minus, you know, it's like 50 counts. There's a little ripple there, but it's almost in the quantization of the feedback device, which is like 1,000,000 counts per rev. So don't put a lot of weight on that. So let's move it out to a kilohertz, and let's crank up the proportional gain. So like a scanning application. There we go. So 1,000 RPM, high gain. So we're going to try to bring the error back down to 0. We got the feed forward term at 100%, so this should bring it down in the integral. Yeah, I could use a little bit more integral. So let's crank it up a little bit. So what I like about this is the other motor I had tested, that Genesis motor, it just required a lot of viscous current. This thing has got pretty low current at 1,000 RPM, and I can't even see the cog in here. It's like it's lost in the mud of the noise, you know. There's a little bit in the following error, but still less. 25 counts out of 1,000,000. That's I'm going to say less than 1% of it's smooth. Like, and we're in the quantization of the feedback device. This is the RLS with 2 to the 20 bits of resolution. So there's some noise in there when the gains crank up. So just maybe get a feedback device, a little less noise, but a good move and settle. The integral's not too high, and the other motor just took forever for the current to get down. It took a long time to settle. So we can get some really fast moving settles out of this. Let's take a look at a slower speed and not go so far. So this is 120. Yeah, so normally if things are going to cog, it's when you go slow and you don't have so much mass on there. But again, less than 1%. I mean, that's just plus or minus hundreds of milliamps. That's beautiful. Look at that. Like 10 counts, 20 count, 10. Like, this is going to be hard to improve with cog compensation. I wouldn't even bother. Right? If you have a cheap motor, poor construction, iron core, not slotless, no Halbach, then that's what you get. Oh yeah, Halbach. There, magnets are arranged such that the field is towards the coil, right? So this is a traditional method, right? That's wasting all this field. You cram the magnets together like north to north or north to north, north to east, north to west, and then all the field pumps out of one side where the coil is. So that's Halbach. And John C. Mallison, 1973. He was born in the UK, moved to San Diego, University of California. Discovered in America, but I guess this guy Klaus gets the credit for this one. Klaus can take the credit, but these physicists all work together. And tell you, I was putting these magnets together like that when I was a kid. So I don't know, 70s. So maybe I discovered it. Anyways, thanks for watching. Take care. Bye.